So to answer this, let's talk about this. What is the square root of 36? How come?
6 times 6.
6 times itself is 36. So what this 3 means is very similar, except for instead of something times itself, it's something times itself times itself again. 3 times. Right? It's the exact opposite of the third power. The third root and the third power, exact opposites. So whereas if I take something to the third power, I want to multiply that number by itself 3 times. Here I want to figure out what number will, if you cube it, if you multiply it by itself 3 times, will give you this number in here. Right? So that number is 4. Why?
4 times 4 is 16, 16 times 4 is 64.
If we multiply 3 fours together, what do we have? We have 64. Is that good, Braxton?
Mm-hmm.
Okay. Maybe that's a new thing, and I wasn't sure if it was new or not. Oh yeah. Any other questions? Keep in mind what we're about to do is take a little quiz, but the way that these quizzes work are they're just a tool for us along the way, rather than at the very end having a big test that you have to worry about, and that's when you find out if you know something. All along the way, we take these like mini tests. Don't affect your grade by very much. You're gonna be graded on this scale, okay? So you can try and just have like an inkling of what you're supposed to do, or what's going on here, and get 2. 3 is most of the way, okay? 4 is tiny mistakes. 5 is perfect, okay? That's how we're gonna score it. But all of these quizzes all together, all go together in a little box, a figurative box, and that box only makes up 5% of your grade, okay? So if you were to bomb every single one of them and not even try anything, I guess you could make the difference between an 85 and a 90, okay? But if you show up every day and you're trying, you're doing your best, you're paying attention in class, you're asking questions during homework time, you're asking questions during class, you're coming in outside of class, don't have some confusion, ready, you'll do well. Yeah?
So I know you showed the work on number 2, but I was confused on that. So can we go through it?
You just want to go through it step by step?
Mhm.
Okay. Okay. Step by step. But, just before this, I have set aside some time to talk about order of operations. So let's just talk about it now at the top. Okay. So we're talking about the order of operations, which, did we watch this video? Yes, okay. So it's really just an agreed upon order. It's not the right order, it's just agreed upon, okay? What does it really do? What does really the order of operations do? Or let me put it this way, if we didn't have an agreed upon order of operations, what would we then have to use to show you what order to do things?
A lot of parentheses.
A lot of parentheses, just like this here, right? Does this guy need all these parentheses? Not in a world where we use an order of operations, right? If we didn't have an order of operations, this is what arithmetic would look like. This is how we indicate the order in which things should be done, okay? But let's now eliminate some parentheses using the order of operations that we've agreed on, right? Of course, versus parentheses. That's just kind of obvious. Parentheses are things that group things together and therefore dictate the order. Okay? So I'm not going to try and break things out of the parentheses before they're done, before I've concentrated my efforts on that parentheses. So that's kind of silly. Exponents, okay, we don't have any exponents, so we go to multiplication. Okay? Let's see what's happening with these parentheses. They are telling me to multiply the 4 times the 5, right? They're grouping those 2 numbers. That's what these things do. They take 2 numbers and turn them into 1 number. So these parentheses are telling me multiply 4 times 5 before, say, you subtract this number, right? So don't take 5 minus this number. First takes 5 times 4. But with the order of operations, PEMDAS, we don't need that parentheses, right? Because in the order of operations, we know that we've agreed. Not we know because we know it's the right thing. We just know what we agreed upon. We've all agreed to multiply before we subtract, before we add. So I don't need that. Okay. With the order of with these parentheses, let's say they're saying group together this 18 divided by 3, divide 18 by 3 before you do, say, the subtraction. Well, we have the order of operations to help eliminate those parentheses, so we don't need to write them because we all agree to do division before subtraction. Okay? So now with the order of operations, I'm not going to try to do 5 minus 18 because we all have this gentleman's agreement that we will not do that. We'll multiply before we add or subtract. Okay? So we're able to get rid of those parentheses. Let's see what other parentheses we can get rid of. So we know we're going to multiply those first before anything else. Multiply these before we do anything else with this 18 and this 3. We're going to take that number and subtract that number from it. And so it's this parentheses is now telling us, take that, subtract that first, and then add this. Okay? But would it make any difference if because addition and subtraction are like on the same order, right? Same level. Would it make any difference if I did 3 plus this number minus this number? Would it make a difference? Let's see. Let's look at like 3 plus 4 minus 5, and I'll put parentheses around it, and then I won't put parentheses around it. Okay? This isn't really an order of operations thing. This is I understand addition and subtraction thing. Okay? So we'll start at 4. So this is 0, number line. Here is 1, 2, 3, 4. So we'll start at 4 and subtract 5. I'm the same, do this first, right? Start at 4, subtract 5. 1, 2, 3, 4, 5. Okay. Now I'm at negative 1. Okay. And then I add 3. 1, 2, 3. And I got into 2. Okay. I'm just kind of moving around. But what if I start at 3, then add 4 and subtract 5? This is really, if I did 3 plus 4 plus negative 5. When I add things, it doesn't really matter what order I do them in, right?
Yeah.
It's called the commutative property of addition. I can switch the order I want. 1 plus 2, 2 plus 1, same thing. It doesn't matter. Or 1 plus 2 plus 3 is the same as 2 plus 3 first, and then add a 1. Okay? And that applies with negative numbers as well. So, like I said, not so much an order of operations thing, just an addition property thing. I don't need these parentheses really. Okay. And now we have a similar thing going on here. I basically add 1 plus 2 first, and then get all of this, and then add what all of that is to the result of 1 plus 2. Would it make any difference if I did instead 1 plus 2 plus then 3 plus then 4 times 5, whatever that number is, minus whatever this number is? By the same thing we just talked about, the associative property of addition, it doesn't make any difference. So I don't need to be told to do 1 plus 2 first. Then in these parentheses, find that number and then add them together. And now we have just parentheses about, around the whole thing. So with an order of operations, we get rid of all the parentheses, right? If we agree to multiply before we add and subtract, we don't need parentheses around 4 times 5. We just agree that we're going to do those first. Okay? That's all the order of operations does. It just eliminates excessive parentheses. So we come along to here. Just do this one step by step. Follow the order of operations. Okay. Let's do what first? Like we should think about parentheses. Let's go on this inside parentheses. 5 minus 2. So we'll do, this is going to be 3 times 3. Add 7 to that. Divide by 4. By 2. Times 2 plus. Yeah. Okay. Should I do 7 plus 3 first or 3 times 3 first? 3
times 3.
Why? Because it's multiplication, and that is right, and to add 7 plus 3 would be wrong. Yeah, but because it's right or because of something else?
Because of the order of operations.
The agreement, yeah, that's what I wanted to get to. I know that's not a very obvious answer. You've probably never heard that in any other math class ever. So, yeah, not because it's right, but because it's per the agreement. Yeah. So the agreement says let's multiply the 3 times the 3 before we add 7. So we'll do that. Also, how about 7 times 2? Is there anything else we're supposed to do before 7 times 2? We're not supposed to do 2 plus that thing, right? No, we're supposed to do the multiplication first. So let's do that too at the same time. Plus, we'll do the 3 times 3 is 9. 4 times 2. All right, what should we do first? We got these parentheses here, right? The only reason I'm going to add the 7 and 9 before I divide by 4 is there's parentheses around it. If there wasn't parentheses around it, I would take 9 divided by 4, right? But the parentheses supersede all, which is kind of a silly thing to say. Of course the parentheses get done before everything else because it's just why we have parentheses. That's why we invented parentheses, was to group things together. After that, 7 plus 9 is 16. 4 times 2. Should we do 4 times 2 first? No. Now what you'll find is some other groups of people have made a different agreement. Okay, and that's where some confusion gets made. Some other people have made an agreement to multiply before division. Always multiply before divide. That's what they agreed to do. Okay? And that's what they view as the right way to do it. Okay? But is that any more right than what we've decided to do? Not mathematically. It's just what they've decided to do. Okay? So we've decided let's multiply and divide on the same level. They have the same power. We'll do it from left to right. 14 plus 16 divided by 4 is 4. And then the result of that will get multiplied by 2, so that's 8. 14 plus 8, 22. Right.
Yeah, I accidentally did the 4 times 2 first.
Before 16. Before
Yeah.
Okay.
And then I divided that and I got 14 plus. Yeah. And then I got
Yeah,
2.
2. Yeah, you know, and that's what this whole string of stuff is putting to the test. Can you abide by the agreement?
Yeah.
It's testing you on. And yeah, it's just about trying to save some ink on parentheses, so we have some walking around money, because we didn't spend all that money on ink. Any other questions from the homework? Let me back up to that homework. Any other questions?
On number 4, like the 5x to the 4th power.
This one?
Yeah.
Yes, okay.
Why is it 5 times x times 5 times x? Isn't it just 5x times 5x?
5x is
Oh, what is 5x?
5x is
5 times x is 5x, so he's just making it.
I didn't have to put that little multiplication symbol there, right? But 5x means 5 times x. So I guess, yeah. You know, that gets to another agreement, that if you see a 5 next to an x, it means 5 times x. Or if you see a 5 next to parentheses, that means 5 times what's in the parentheses. Like, no symbols needed. But absolutely, yeah, 5x. I can even just write 5x, 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 5x. I just wanted to be clear. But if I see an x next to a 5, that also means multiply. Yes?
So it's not wrong if you did 5x times 5x?
No, this is right. Any other questions? It's a good question. Alright, again, if you have no questions, it means you are telling me I am ready to show you on this quiz type thing that I know what's up. Ready?
So if we get something wrong, we just redo it, and then.
On the homework?
Yeah.
The homework I'm looking to see that you, I've already gone through and assessed whether or not you tried. Okay?
Okay.
The only reason you're gonna lose credit is you just left stuff blank, didn't even give any effort, because you decided, I don't know, you're too sleepy. You could be too sleepy, but you're gonna lose credit because you didn't do it all. But getting it wrong is not how I grade the homework.
Okay.
And if you make a mistake, feel free to just keep writing on it, correct it for later, just for your reference. Any other questions? Okay, then in about 5 seconds, I'm gonna ask you to pass your homework, and I think everybody had their homework, right? If you didn't have your homework, which isn't the case today, you would need to do what?
Pink slip.
Get a pink slip and turn that. Okay. If that's not the case, then let's just talk about it in our homework, please. Okay, let's start out with this one. Let's put it to a vote. Do we think that we can simplify it? Possible? Thinks we cannot simplify it. All right, not everybody voted. That's okay. So let's start from the mindset of this could be simplified. If it could be simplified, we want to cancel something out, right? What do we want to cancel out then? What do we feel like might cancel out? X squared. Okay, let's try x squared. Now keep in mind, let's just remind you real quick, let's do 30 and 55, right? Can that simplify?
Yeah.
Yes, because 33 and 55, 11 is a factor of both, right? That's key, factor. So how we define factor as if it were some kind of a big deal. Because it is a big deal what a factor is. What we mean by that is 11 times 3 is 33, and 11 times 5 is 55, and 11 divided by 11 is 1. Okay? Not 11 is there, and 11 is in the denominator as well, and we just put lines through them and they disappear, but 11 divides 11. So if we're going to cancel out x squared, it needs to be possible for x squared to divide x squared, which means we have got to be able to write x squared over x squared times what will then be our simpler fraction. Okay. Let's start in the denominator. Multiplying straight across, of course. X squared times what will give us x squared? 1. Let's start up here now. Keeping in mind we know something about distribution. We're going to talk about distribution a little bit more in depth today, but we know that we have to distribute this x squared to something, to something, to something else. Right? To each thing. Okay. So what would we distribute it to get x squared? 1. And what would be next so that x squared times that thing is 4x? 4x? Let's check that out. What's x squared times 4x?
4x cubed.
Yeah, see what, I mean, it's not like anything we have to memorize or understand too deeply, but x times x is, x squared. It's an x times another x, and you know what I'm going to multiply by another x? That's 3 x's. So that'd be x to the third, and then of course we have that 4. So, maybe instead of like going, this is bad math terminology, but instead of going down in x's, we went up in x's, right? We need to lose an x somehow, because we have an x squared, we want to wind up with a 4x to the first.
It would have to be 4x over x.
4x over x? Think about 4x over x real quick. X would divide x, we'd have 4, right? But we're on the right track there. Something has to eliminate that x squared.
What if you just did if you just try to get rid of 1x?
Let's try that in just a second. What we'd have, I'll just cut to the chase. In order to cancel out that x squared, you have to have 4 over x squared. So that x squared would get divided by x squared, leaving 1, and then that times 4 leaves 4. I'm sorry, just 1x in the denominator, just x to the first, not x squared. But then we'd have to do 1 over x squared in order to accomplish multiplying by x squared and winding up with 1. Okay, so let's back it up. Let's try 1x. I like that. I like that idea. Okay, so we want just 1x. So we have to multiply by what in the denominator? X. Okay. X times something is x squared. X, okay. X times something is 4x. This is looking more promising. X times something needs to be 1. What would that thing be? X times something equals something that doesn't have an x in it. You see the challenge there? 1 over x would do it. But is that simpler is the question. Is that simpler? No. You ask yourself this. If I needed to plug 5 into, so this would divide, and like the new fraction would be this. If I had to plug 5 into either this fraction or this fraction, which would you choose? Which you then have to simplify down to the final number, first one. Because you know what you'd have to do here? You'd have a 1/5, and you have 4 plus 5, that's 9. So you have to add 9 to 1/5, which means you need a common denominator. Then you'll have a fraction in the numerator of a bigger fraction, then you'll have to deal with that. Okay? What we could do instead is just plug 5 in here, and it takes care of the whole thing. So there's your thing. Doing it the way that I'm asking you to will force you to realize you have to distribute that thing across this, what we hope is a simpler numerator or denominator. And if it doesn't work, if I can't get to distribute over something simpler, then I'll just say it's as simple as possible. So we'll say like, no, or not possible, or it is simple, or like just a big cross through it, like some kind of indication that they realize that it cannot be simplified. Because that is the answer, right? It's not possible. Let's go on to this guy. What do you feel like could cancel out? And then we'll have to write it just like 3x. Let's just go for the goal. Just do everything all at once. 3 times x. If it's possible to cancel out that 3x, it's because it's a factor of the numerator and a factor of the denominator, and a factor means I can multiply it by something else, right? 3 is a factor of 15 because 3 times 5 is 15. So, is 3x a factor of the numerator? If it is, we can distribute it across something and get the numerator. All right, so let's start with 3x squared. What can I multiply 3x by to get 3x squared? What?
X.
Just an x. 3x times x is x squared. Great. Next, we need to multiply 3x times something and get 12x. 4? 4? 3x times 4. 3 times 4 is 12. We get that factor of x. Great. Now we just need the denominator. Looks like it's going to be easy. 3 does work. We are able to cancel out a 3x. We are already able to get 3x to divide 3x, leaving us with 1 times our new simpler fraction. Okay, so let me just, let's talk about the scoring system real quick. They, say they just canceled the 3, but that like there's still an x in there, they didn't cancel out the x, it'd be like a 3. Okay? They really get what's going on if they've done this. If they know that they can cancel a 3, they just miss the x. Right? That would be a conceptual mistake. The concept being they don't really understand how to fully simplify it. They do get the idea that whatever the thing is, like if they have x squared plus 4x over 3x, they understand that something needs to be divided out, not just look the same and cross it out because it's the same. They get that. Just don't get it all the way. It's this guy. Okay, so number 3. Right, yeah, number 3, we're ready for that. How would we write this out the long way? The math term, yes?
Maybe 5 times x times x times x times x.
Right. I could write it like this, I could write it times in between all of them. Like, that's understood to be times. When you just write numbers next to other numbers, that's multiplication. Or they could have those, they could have these, you have parentheses around every x, whatever, indicates that all those x's get multiplied.
Can you do negative 5x times negative 5x and so on and so forth?
Well, is negative 5x times negative 5x times negative, is that the same as this? As what I have here? No, because there's all those factors of 5, right? So the first thing we need to notice is those are different things. And so why should we arrive at this and not at negative 5x times negative 5x times negative 5x? Well, this exponent of 4 means multiply something by itself 4 times, right? So now it's just a question of what is it that I want to multiply by itself 4 times? And I guess it does come down to an order of operations thing, because if we didn't have an order of operations, I kind of wouldn't know what to go for first. Should I multiply the negative 5 by the x and then take that whole thing and multiply by itself 4 times? Well, by the order of operations that we've agreed to, no. Okay? We've got exponent here, applying to the x, but not to the negative 5. Okay, so let's come over here and talk about how would I get negative 5x times, let's use a parenthesis, negative 5x times negative 5x times negative 5x. How would I change this slightly so that this did happen?
And parentheses around the negative 5x, not the 4th outside the parentheses.
Okay, so let's put parentheses around this entire expression and then take that to the left. Now I want you to, indicated by my parentheses, take that entire term and multiply by itself 4 times.
That makes sense.
What if I wanted, instead of like 4 negatives to multiply, what if I just wanted like a negative out front right? Just negative 5x times 5x times 5x times 5x. What could I just do? Just like, I don't even have to write anything new or erase anything. I can really just like move one thing.
Move the subtraction sign outside the parentheses.
There we go. That would be different. Okay. Or I could have moved the parentheses in so that the negative was out or whatever. So now the fourth power is telling me to multiply something by itself. What is the thing that I want to multiply by itself 4 times? Now it is just the 5x, and then, you know, throw the negative on after you're done with that. This guy right here, it's a little bit of a test of your remembering of the order of operations. The exponent is first. It applies just to the x because I have not put parentheses around anything. It's just the x. And then when I'm done with that, I'll multiply that by negative 5. And like questions like this is what these quizzes are all about. Is to figure that stuff out.
So if you were to put parentheses around just the x, would you still be just doing?
Would it be the same as this?
Yeah.
Yes. Essentially, there's like an understood parentheses around the x. And there's really just an understood parentheses around this whole thing, right? Do this first. Well, because of PEMDAS, we do that anyway. We do exponents first. Right, great question. Any more questions about that? I love questions. The most important part of learning. All right. If no more questions, we're going to go to this guy here. And I'm going to make a little more room for it. Copy this page. Okay. Just make sure we adhere to the agreement. According to the agreement, we should go to the innermost part of the parentheses. I don't even know parentheses should be part of PEMDAS because it's just so obvious that we would do parentheses first. But anyway, let's go within the parentheses and then within those parentheses, and if there's more parentheses inside those parentheses, let's just keep going down, 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 you know, parenthesesception to the very furthest inside parentheses. And inside this most inside parentheses, what should we do first?
Times 2.
3 times 2. Why don't we do 4 plus 3? Because that's not what we agreed to, right? It's about the agreement, as was said before. So we'll do the 3 times 2 first. That's 6 plus 4. Let's kind of look for anything that we could also do at the same time. I don't know if there is anything. And it doesn't seem like it. Plus 1, 8, 4. Oh, can we multiply this 8 times 4? Why not?
There's division first.
Because there's division before that. I'm supposed to divide 8 into the result of these parentheses, right? I got a while before I do any multiplication by 4. Let's keep going. 3 outside here. 6. Okay, what can we do next?
7 is
4 plus 6.
4 plus 6, we can do that. That's inside the parentheses. That's 10. 7. 5 there plus 1. 8, 4, 7. Oh, maybe we should do this 2 minus 6. No, Ian, why not?
Through the parentheses first.
Wow, that's a good point. Let me go back to this, to the original homework problem, because we worked one of these out. Wait, we worked it out on a separate one. There it is. Take a look at this. Before this parentheses was all the way done, we did 7 times 2, right? Right? So it's not so much.
Because it doesn't affect it, or?
Yeah, this doesn't, the multiplying by this needs to happen before adding this, right?
It doesn't really matter.
So, I mean, that's gonna, even when I get all done with the parentheses, I'm gonna have to multiply these together first. Let's see if that still applies here. Yeah, this is where we are. Should I do 2 minus 6 first? Why not? Not because of parentheses, but
Because there's
because,
the times 3.
because the negative 6 here is multiplied by a 3. I want to multiply by that 3 before I subtract it from 2. Not because it's the right thing to do, but because we agreed to do it that way. So could we multiply the negative 6 by 3? Would that affect anything in here? It would?
I don't think so.
Imagine 2 scenarios, one where I multiply these together and then work out the parentheses, and one where I work out the parentheses before I multiply the negative 6 times 3, aren't I going to have to multiply the negative 6 by 3 before I multiply it by the parentheses? What?
Do you have to multiply the 3 by the parentheses?
Well,
What 6 has to be
so we're getting
multiplied
into,
by
it
3.
could get a little confusing here, but it's not that bad. What you have is a negative 6 times a 3 times whatever this number is. Yeah? Now, if I do 2 times 3 times 5, just as an example, does it matter if I do 2 times 3 and then times 5, or 3 times 5 and then times 2? Does that make a difference? It does. It's called the associative property of multiplication. I could do them really in any order I want. So we could multiply the 3 into the parentheses and then multiply by negative 6, but it would be the same as if we multiplied negative 6 by 3 and then multiplied that by the parentheses. And if we just go by the order of operations, then we do multiplication and division from left to right, and this is on the left, so we can do that first, right? So you can just multiply the negative 6 times the 3 and the negative 18 now is the thing. We'll multiply by whatever the parentheses produces. 2 minus 18 times. We got stuff in the parentheses to work out. 5 minus 7. What should we do first?
Negative
Multiply.
7 times 10, right? Per our agreement, we're going to multiply first. 5 minus 70. 1 divided by 8 times 4. That's good. Now, 2 minus 18, no, because there's multiplication going on here, so we don't want to do that. We should keep whittling away at the parentheses. Let's just do all this at once. Like, could I do 5 plus 1? That's okay, right? It's really 5 plus negative 70 plus 1, and there's this commutative property of addition. It says we can do it in any order we want. 2 plus 5 plus 7, for example, is the same as 2 plus 7 plus 5. Switch it up like that. Okay. So, like 6 minus 70. 60, not 54, 64. By 8, times 4, 7. All right, let's keep moving. What's next? Negative 18 times negative 64, and that should be positive. So we're going to do 2 plus a number, and that number is 1,152 divided by 8 times 4 plus 7. Along here I see some division and multiplication, so I should have to do something before I add. Divide by 8 first. That's 1,152 divided by 8. Is that? 144. We multiply that by 4. That's 7. Go horizontal here, because I'm in space. Multiply first, 144 times 4, not 2 plus 144, that's not the agreement. What's 144 times 4? 576. Plus 2 plus 7. So 585. There you go, 585.
That's 5, right?
Could you tell where like it counts for something?
Alright, so that's the last one. Score out of, there's 4 questions, 5 each, 20 points total. Okay, if you feel like you just can't quite make the call between a 3 and a 2 or a 4 and a 3, just leave it to me because I'm going to look over these as well, which should be also good news if you feel like the person grading your quiz right now is being unfair. You can be sure that I'm going to be fair as possible. Okay. It's a good exercise for you to look at somebody else's work, see what they've done, try to assess it out of 5. You know, makes you really think about the math.
Yeah.
So now we're going to talk about the distributive property, okay? The goal is not to teach you the distributive property. I'm pretty confident, because the distributive property is not a hard thing to do, but to understand why we do it is important. Because when we go to multiply things called polynomials, you guys know what polynomials are, right?
Heard
This
it.
is a word that you know of, right? We need to multiply polynomials by each other, and starting with the most simple polynomials, which would be just some numbers, it's much easier to see why we do this distribution. Okay? And what happens when we have not just 5 times 3 plus 4, but 5 times 3 plus x. And not just 5 times 3 plus x, but maybe 3 plus x times 5 minus x. Right? When we start to build those things together and multiply those together, then this picture that we're about to draw helps out a lot. Right? So let's start easy with this example, then a simple example with an x, and then when we need more advanced, we'll refer back to what we've already talked about today. So we're going to look at multiplication. That's what we're doing here, right? So we're multiplying. So I'm going to use a picture to show you multiplication. Anybody think of a way that I can use a shape to show you multiplication? Can anybody think of how I could use a rectangle specifically to show you multiplication? What about a rectangle could show multiplication?
If you have like 3 little rectangles together and you do 3 times 5, then you take those 3 little rectangles and you duplicate them and make another rectangle.
Okay.
3 times 5 is now 35 little rectangles.
Okay, that's the right start. I'm going to use just a single rectangle, and instead of like having a bunch of rectangles, I'm going to have a bunch of squares. And what I'm getting to is the area of a rectangle, right? Isn't the area of a rectangle? He's right.
I was right. That was 1 times 35.
Yeah.
I don't
Oh my
Okay.
god.
We have a connection. I don't know about that. But I get you. But I'm just going to use a single rectangle, and I'm going to show you 2 times 3, right? It's about the simplest of multiplications we can do. All right? So a rectangle that is 2 by 3 can show us what 2 times 3 is. 2, 3 here. Okay, let's say like this side over here is worth 2. Right? And I want 3 groups of 2, and so now I see 6. Right? Simple. 2 times 3 is 6. That's what I want you to see. We have to do multiplication over here, right? We're going to start with the idea that length times width can show us multiplication. Okay, so now I need to show you a rectangle that represents this situation. All right, you ready for that? Of course you are. So, let's see, I'll make this side 5. 1, 2, 3, 4, 5. Okay, let's start with that one, that one's simple. Now I'm going to make this side equal to what's in this parentheses, 3 plus 4. I could just draw 7, but I also could draw 3 and then another 4, which is what I'm going to do. So 1, 2, 3. There's my 3. Right there. Right there. And here comes the 4. Plus 4. Plus 1, 2, 3, 4. This part is 4. And there's my rectangle. And the area will show me 5 times 3 plus 4. Okay. I could add 3 plus 4 and get 7, and 7 times 5 is 35. Absolutely. Okay, but I want to show you why we have to distribute across this addition. It only makes sense. Right. To get the area of this rectangle, a part of it is 5 times 3. So the area of this rectangle will give me the 5 times 3 part. There's 5 times 3 right there. Well, the rest of the area of the rectangle is this much area. What's the area of this rectangle? 4 times 5, or 5 times 4. Right? And how do I get the total area of the rectangle? Add it up, right? Because I want to get the total area, so I want to take this area and add it to this area. So one way is 5 times 7, but another way is 5 times 3 plus 5 times 4. So there you go. There's a distribution across a couple of numbers. Now let's look at distribution across something with x in it. Now here's the challenge. Thinking about x. Having a picture of x. What is x? An unknown. So if I draw a rectangle that is side length x, that's going to be a difficult thing. We gotta kind of suspend our disbelief and realize that when I draw this length x, it could be any length, right? And I won't mark it off like I would like a ruler or whatever, because I don't know how big it is, but I have to pick something. I'm gonna use something for this picture. Okay, so let's look at 3 times 4 plus x. Different kind of problem. Well, just like this side I'll make 3. And then I'll make this 4. 1, 2, 3, 4. Okay, so here's my 4. And now I'm going to draw x. Now I can make x this big. I can make it this big. This big. I can make it just out into the parking lot and down the road. Like it could be any length, right? But I have to draw something. Which is kind of the bummer about this. So we'll just draw it. Don't worry about trying to measure it and figure out how big it is. That's not the point. Whatever it is, it's subject to distribution. That's what we're trying to get across here. Whatever that number is, it's going to have to get multiplied by 3, and that's the point. Okay, so here is one part of the multiplication. That is 3 times 4. All right. This side is x. This side is 3. How big is the area of this rectangle? 3x, right? That's the only way we can say it. We say it with algebra by using a variable. 3 times x. This could be 7, this could be 12, this could be 156, whatever it is. What would we do with it? We multiply it by 3. So 3 times x, and this is 3 times 4. Okay. So 3 times 4 plus 3 times x. There's a distribution, 3x plus 12. Okay. But now you see a picture of why it has to be. It could not be any other way. There's no question there. And when we go to do something like, I won't do it right now, but you could imagine if we did x plus 2 times x minus 5, and what if we also did x squared plus 9x minus 7 times x to the 3rd plus 2x squared minus 5x minus 17. Okay. Just drawing a simple rectangle can see it, like help us see why we do what we do. So that's where we're going to stop with distribution for the moment. Does that make sense? That picture make sense?
The picture did, yeah.
Is there any question that you could ask that I could answer that would clarify it at all, Brennan?
Wait, I was just figured out another way that's kind of cool how you can multiply with square.
Okay.
So you draw a square.
Yeah?
Yeah. All right. No, you gotta draw it bigger.
Oh, I gotta draw it bigger.
Yeah.
Yeah, let's just go on to the next page
Yeah.
and then I'll draw a big old
Draw
square.
like a big old square.
Okay.
And now whatever 2 numbers you want to multiply, like let's say 3 and 4, simply you put 3 dots on that side, just anywhere. Yeah, and you put 4 dots on the bottom.
Oh,
Or top.
whatever, I guess.
And then you make those 4 dots hit the perpendicular line above it. So you just draw a line from that dot up to the top of the square.
So it's
Yeah.
a lot like the last one.
No, wait. No, wait. This is good.
Okay.
Now come back down. Yeah, just keep doing that
Just
with
do,
all of them.
okay, do all of it like this, and then of course this way.
Yeah, and then it's not blocks, you count the intersections of lines.
Okay. And it's the same concept, but it's
Yeah.
it's different too, right? So yeah, we just count these.
So it could be this.
And you know, if I put like a little square around each of these, you know what I'd have is just what I did with the rectangle and the squares. So we're counting the same way.
Yeah, then you're good.
Just a different form.
Yeah. There you go. If you like that, that certainly would work as well. It'd be hard to show x with dots. Though it's,
Yeah.
it's hard to show x with side lengths too. Okay. Thanks for sharing that. I like when,
Good job, Brennan.
when we try to add to the class, not take away. Okay. So let's talk about algebra. What makes algebra, meaning it's different from some other math?
Unknowns.
Unknowns. You know, your most basic math, which I would really just call arithmetic, it involves all numbers, just number crunching, 5 plus 3 divided by 6, and all the numbers are known. Now, what's algebra about algebra is we use letters to represent numbers. I found an interesting TED Talk that I thought you might think is cool. TED Talks. You know what? If you don't think it's cool, you're going to watch it anyway, so might as well enjoy it. It's probably loud enough, huh?
Maybe.
Less loud.
I have the answer to a question that we've all asked. The question is, why is it that the letter X represents the unknown? Now, I know we learned that in math class, but now it's everywhere in the culture. The X Prize, the X Files, Project X, TEDx. Where'd that come from? About 6 years ago, I decided that I would learn Arabic, which turns out to be a supremely logical language. To write a word or a phrase or a sentence in Arabic is like crafting an equation because every part is extremely precise and carries a lot of information. That's one of the reasons so much of what we've come to think of as Western science and mathematics and engineering was really worked out in the first few centuries of the Common Era by the Persians and the Arabs and the Turks. This includes a little system in Arabic called algebra, and algebra roughly translates to the system for reconciling disparate parts. Algebra finally came into English as algebra. One example of my many. The Arabic texts containing this mathematical wisdom finally made their way to Europe, which is to say Spain, in the 11th and 12th century. And when they arrived, there was tremendous interest in translating this wisdom into a European language. But there were problems. One problem is there are some sounds in Arabic that just don't make it through a European voice box without lots of practice. Trust me on that one. Also, those very sounds tend not to be represented by the characters that are available in European languages. Here's one of the culprits. This is the letter sheen, and it makes the sound we think of as sh. Sh. It's also the very first letter of the word shay'un, which means something, just like the English word something, some undefined, unknown thing. Now in Arabic, we can make this definite by adding the definite article al. So this is al-shay'un, the unknown thing. And this is a word that appears throughout early mathematics, such as this 10th century derivation of proofs. The problem for the medieval Spanish scholars who were tasked with translating this material is that the letter sheen and the word shay'un can't be rendered into Spanish because Spanish doesn't have that sh, that sh sound. So by convention, they created a rule in which they borrowed the ck sound, the k sound, from the classical Greek in the form of the letter chi. Later, when this material was translated into a common European language, which is to say Latin, they simply replaced the Greek chi with the Latin x. And once that happened, once this material was in Latin, it formed the basis for mathematics textbooks for almost 600 years. But now we have the answer to our question. Why is it that x is the unknown? X is the unknown because you can't say sh in Spanish. And I thought that was worth sharing.
Okay, so that's it. I mean, I don't know how useful it is for us in algebra, but it's a question I always had, and then this guy explained it. And if he's right, then it's kind of interesting. Okay, so we use x a lot in algebra, but we can also use a or b or m or n or anything you want. All right. So that letter X or whatever represents some unknown thing. So I could say something like a number plus 5, or 5 more than a number. How would I represent that with algebra and symbols? A number plus 5. That's back to 5. Okay. So that's it. That's the most basic thing about algebra. And I could say something like, I have $8 more than some other person. Okay? How would I show that? Represent that with algebra symbols?
P plus 8.
P plus 8. P. Why P?
Some other person.
Some other person has some money, and if you take the amount of money that they have, and you add 8, then you have how much money I have. Okay? Or if you say that Brennan, right, is 4 times as old as, let's say, Oliver, just make somebody up. How do we represent this? How old Brennan is? Mitch.
B is equal to 4O.
Brennan is equal to 4. Oh, I don't know. Oh, do you see any confusion that could happen?
Yeah, or it's like 40.
Yeah, it would look like 40. So for that reason, O is not a very popular thing to use.
X.
X.
We just call him X Oliver.
X Oliver.
It's the
X Oliver.
That's cool, man.
It's Oliver.
weird.
It's Oliver.
Oliver.
So Brennan is equal to 4 times Oliver, right? And when we say Brennan and we say Oliver, we mean their ages. These are the most basic things in algebra you do. And in the homework, there's some very simple, maybe 1 or 2 operation statements like this that I want you to put into algebra, just using algebra symbols. That's about, let's see about that. But it's just as basic as that. That's all algebra is. It's, as that guy said, reconciling the method by which we reconcile disparate parts or something like that. There's this thing that we don't know, and algebra is the way that we find it. And the first part in that is writing it down. Okay. So let's talk about an algebraic expression. An expression you can think of as just a collection of numbers that we are trying to combine with addition, subtraction, multiplication, and division. Exponents or square roots or anything. So an algebraic expression is something like that has variables in it. So I'm going to write just a nonsense algebraic expression that has no meaning, but it helps us talk about different parts of an algebraic expression. The only reason we're doing this is so that later when I say a word, you know exactly what I'm talking about. All right. So if I put some boxes around this -2 and this +3, what are those 2 things? There's a word for that. Coefficients, great. I had plenty of classes that did not know that. That's a coefficient. If I put a red box around this, and this, what are those? Variables. They're the variables. A blue box around this, and this, and this. What are all 3 of these? Very good, terms. We use the word term a lot, and yet it can be confusing if you have not well defined what a term is. So a term is anything that has like its own sign, it's its own number, it's like the result of some multiplication or division, you know, that something in the order of operations groups it together. It is a term, and then it would be added or subtracted from or to another term. Okay, so that's a term. And we have variable terms, terms with variables in them. So if those are variable terms, then what would that be?
Coefficient term.
Yeah, it looks like a coefficient just hanging out by itself.
Constant term.
Constant. No, you're not. Yeah, it's a constant, right? It doesn't vary. The opposite of a thing that varies is a thing that doesn't vary. It's a constant. It's constant. So we got our variable terms and our constant term comes from here. So those are all the parts of an expression, things that you definitely be expected to understand. So now let's talk about what makes terms like terms. All right? And I'll start by showing you a mistake that happens a lot, right? Just something that is helpful to see a mistake. Let's say we had 5x squared plus 4x to the third. Here's something I see quite a bit. That would be, we get 9x to the fifth. Right. Ooh, that's not. What does x to the fifth mean? X, right? Is that happening over here? We do have 5 x's over here, right? But the problem is 3 x's are getting multiplied together and 2 x's are getting multiplied together, and those groups are being added together, not multiplied. Right? We have 5 times x times x times x. We have 4 times, sorry, just 2 x's there, not 3. Plus 4 times x times x times x. It almost looks like x times x times x times x times x, but it's not. There's addition between them. So it's not the same thing as multiplying 5 x's together. It's not 9x to the fifth. So, are these like terms or not like terms? Not like terms.
Wait,
Yes.
if you write them out, like completely though, like 5 times x plus 4 times x times x times x.
Yep.
Couldn't you combine the 5 and the 4 in that group, considering they're like terms?
Let me just take back what I just did.
We want the 5 and the 4 to be like terms now?
Well,
Not-
no, and that's because, due to the order of operations we all agreed to, there's an understood parentheses
Okay.
around these guys. Meaning, here's a term over here, here's a term over here. We have to wait until the multiplication is done here and there before we add them together.
Okay, yeah.
But once we put something in for x, and now we're just gonna have 2 numbers, whatever the result of that is, we can add those together. Okay. So, let's do this. So they're not like terms. And I just want you to think about this in a common sense way. It's really kind of back to trying to add fractions that don't have a common denominator, right? You don't need to find a common denominator or anything. We can't even put these together. The thing is, we can't put them together because of the same common sense that these are not the same thing. This is apples and oranges that we're trying to put together. You're not gonna put apples and oranges together and have 9 apple oranges, okay? There's just no way to put them together and make an apple and an orange combine into 2 of the same thing, okay? So, if I were asked to simplify this, I would just say, well, it's simplified. There's no adding of like terms here. They're not the same kind of thing. This is 5 of one kind of thing, and this is 4 of some other kind of thing. All right? This is, let's say we put a, I don't want to say a number here, so like a 2, okay? We put a 2 there, and 2, of course, would have to go into the other x when we put something in for one x. All the x's are the same number. So, we have 5 times a 4 plus 4 times an 8. This means we have literally 5 4s, and here we have 4 8s. Right? I don't have 9 of anything. I have 5 4s and I have 4 8s, and to put that together and say we have 9 of something would be like trying to say 9x to, I don't know, the 5th or the 6th or something that doesn't make sense. So we can't put them together, we can't add them because they are different things. Completely different things. So, if I did want to add something to 5x squared, what would that kind of thing need to be? What kind of thing would this need to be in order to be added to 5x squared? A like term. What makes it like a 5x squared?
Another something x squared.
Another something x squared, right? I have 5 squared x's. If I want to add something to squared x's, I need some more squared x's. If I want to add something to apples, I need some more apples, right? So I could add 4 of these guys. Okay.
You don't like every remainder more?
What's that?
Because it was cubed, don't you?
Maybe I shouldn't use these numbers. This doesn't have anything to do
Oh,
with this.
okay.
This is an example of like terms, this is an example of not like terms. So, but I totally see that can be confusing, so let's just make that set on there. Not like terms. I like to make little notes like this in case anybody downloads the PDF. Try to So here I have an x squared, and here are 5x squareds, and I have here 7 of those same kinds of things. So I can put them together. I have 12 of those things. I have 12 squared x's. So I just want to give you intuition. When I really want you to have intuition about all of the things that we learned about. If you just have rote memorization of stuff, then you're really at a disadvantage. And now's the time to strive for intuition about these things. It's the beginning of the year. If you have to relearn some things, I really highly recommend it, because as we get down the road, you'll have to trust me, this is going to be a better way to think about it. So, to add like terms, they've got to be alike, they've got to be the same exact thing. Here, let's see. Do it. Yes. Let's collect like terms, simplify that expression. Can I subtract 4x squared from 7x cubed?
No.
Okay. Why? And don't tell me because they're not like terms. Why?
Different exponents.
Okay. That's a rule I can follow.
1 cubed, 1 squared.
1 cubed, 1 squared, different exponents.
Agree.
At an intuitive level, even if I try to put, subtract 4 from 7 to get 3, what's the problem with that?
You still have to deal with the x's there too.
3 of what? It's like having 7 oranges and trying to take 4 apples from that. That's impossible. They're not apples. I can't take them. Okay? So I have 7 oranges and I try to take 4 apples away. It doesn't make any sense. I don't have 3 of anything. I have to take oranges away from oranges in place. Okay? They're just completely different things. So let's look through, and we'll write it in order so that the highest power comes first, just because that's kind of a normal thing to do. There's no other oranges. These are the only oranges that there are. So they're all alone. Okay. There's some apples. Are there any other apples that we can combine these apples with? Yeah, there's some 9 over here. So we can take 4 of these from 9 of those, and we have 5 of those. Okay. We have some kiwis. 2 of them. And then we have just some numbers, right? You may feel like this is just overstating a point, or you may feel like it is boring, or you feel like a lot of things, but I can't tell you the number of times that I watched someone on the test just continue to put this together and get 12x to the 5th, and to put that together with that and get 14x to the 6th, and then add 7 to that. Just, I want you to at an intuitive level say, these things aren't the same. Why would I even try and add them together? They're different things. Just leave them. Okay? Yeah, that's our time.
Yeah.
Right now.
It was.